Hi everybody, today's lecture is about electricity. Let's get started. So electricity is a subset of electromagnetism, and next time we'll talk about magnetism. This time we'll talk about electricity. So there's a lot of different phenomenon for electricity and magnetism. Electrostatics is the study of electricity at rest. Electrodynamics is the study of electricity in motion. Magnetism is the study of motion of charged particles with magnetic forces and fields. And electromagnetic induction is the study of how changes in electric field create magnetic field and vice versa. Okay, so this is sort of an overview of electromagnetism. This is sort of everything we'll cover in the next two lectures. Okay, electric charges. So electric charges can be positive or they can be negative. The unit is a coulomb. So how much charge does something have will be given in the unit of coulombs. All the electrons of all the atoms are identical. So every single electron you ever interact with is identical to every other one. Don't know why, it just is. Each has the same mass and same negative charge. So electrons have negative charge. And nuclei are positive charge and are composed of protons and neutrons. So this is an atom. It's got 2 electrons and a nucleus with 2 protons, 2 neutrons. That looks like helium, helium-4. Okay, the electrons are negatively charged, the protons are positively charged, and the neutrons have no charge. Okay, the reason why positively charged nuclei do not pull the negatively charged electrons lies in quantum mechanics. We're not going to talk about that right now. We'll just skip that paragraph. You can read it if you'd like. Charging happens by moving electrons from object to object. So if I move electrons from one object to another, then I can build up negative charge in one object and decrease negative charge in another, building up positive charge. Electrons are the main charge carriers in nature. Sometimes other things move around, but generally it's going to be electrons, the charge is moving. Okay, there's the idea of conservation of charge. Let's just read this here. In any charging process, no electrons are created or destroyed. Electrons are simply transferred from one material to another. So this is similar to conservation of energy, except in this case it's charge. Okay, and since electrons are the primary movers in nature of electricity and charge, we can talk about electrons being the thing that transfers charge around, so no electrons are created or destroyed. Okay, when you brush your hair and scrape electrons from your hair, the charge of your hair is, since we're scraping electrons from your hair and putting them in the comb, then the electrons are leaving the hair and going into the comb, and the charge of your hair will be positive, because electrons are getting pulled out of the hair. Okay, charging by friction and contact. So stroking cat's fur, combing your hair, rubbing shoes on a carpet, all of these different friction situations can cause electricity, can cause charge, static charge to build up. And then, so this is caused by electrons transferring from one material to another. Okay, we can also charge by induction. This is if you have a charged object and you bring it near a surface that can conduct electrons. So if we look at the bottom, if we have a storm cloud here, if negative charge gets built up on the bottom of the cloud and positive charge gets built up on the top of the cloud, then the ground, because it's close to the negative charge, will build up a net positive charge. So it's an induced positive charge due to the closeness of these negative charges in the cloud. Okay. So let's just walk through this example by induction, charging by induction. So you've got this. We're going to go through these processes here. So we've got things A and B. They touch each other, so in effect they form a single uncharged conductor. So this is A and B are 2 conductors, meaning the electrons flow freely through the conductors. So what we want to do is first have them touch, so that they're completely neutralized and they have no net charge. So, and then step B is when a negatively charged rod is brought near A, electrons in the metal, being free to move, are repelled as far as possible until their mutual repulsion is big enough to balance the influence of the rod. Okay, so we bring a negatively charged rod nearby. This pushes the electrons from sphere A into B. So that leaves behind a net positive charge. And the electrons running away from the negative rod build up a negative charge on sphere B. So these are induced charges here on A and B. So part C, the charge is redistributed. So we pull the spheres apart, And then A has a net positive charge, B has a net negative charge. And then we pull, if A and B are separated, when the rod is present, each will be equal and oppositely charged. Okay, and then if we remove the rod, then A will have a uniform charge and B will have a uniform charge, one positive, one negative. Okay, so we can do this charging process by induction if spheres A and B are conducting and we have a charge rod to work with. Okay, charge polarization. Let's read this. An atom or molecule in which the charges are aligned with a slight excess of positive charge on one side and a slight excess of negative on another. So if we look at this balloon has a negative charge, if you bring it close to the wall, it pushes the electrons away, which then causes a row of positive charge and a row of negative charge. We get this charge separation, and that's called charge polarization. Okay, so this is an example. Let's walk through it. So rub an inflated balloon on your hair and it becomes charged. So we charge the balloon. Place the balloon against the wall and it sticks. This is because the charge on the balloon induces an opposite surface charge on the wall. Okay, so the negative charge on the balloon pushed the electrons away, leaving a remaining positive charge, so it sticks. Again, closest wins for the charge on the balloon. It's slightly closer to the opposite induced charge than to the charge of the same sign, so we get sticking. Okay, and the balloon caused charge polarization in the wall. We'll talk about charge polarization a little bit more in a few more examples. Okay, so if we look at this, let's start with this picture here. We've got it looks like a hydrogen atom with a proton and an electron cloud. Right now, the positive charge and the cloud are completely lined up. If we offset them, so the negative charge is centered somewhere not on the proton, then there's a charge polarization because we separated the charge. Let's look at this picture down here. If we have some polar molecules, so one end of the molecule is positive, one end is negative, and it's free to rotate. If we bring a charged rod nearby that's negatively charged, the positive charges are going to rotate toward the rod and the negative charges are going to rotate away from the rod. And because they're all lined up like this, that's called charge polarization. Okay, so the wall here, when we separate the charges, that's charge polarization. When we offset charges in a hydrogen atom, that's charge polarization. When we get these atoms lining up because of a charge nearby, that's also charge polarization. Okay, and then here's a water molecule. So this is a proton. These are it's a hydrogen, oxygen. There's more positive charge up here and more negative charge down here. That's how a water molecule works. So we get this charge separation, positive up here, negative up here. That's a charge polarization. So we call water a polarized molecule. And those molecules that have polarization are called electric dipoles. Okay, let's talk about electric force, or the Coulomb force. It's very similar to the gravity force. If we look at this it's an equation down here where the force on two charges, Q1 and Q2, separated by a distance d, is given by this formula. And the constant is K here. Before it was big G, that's the gravitational constant. Here it's K. And K is this huge number with these units here. Okay, if you compare it to the universal law of gravity, instead of big G, it's K. Instead of charge, it's mass. And force is force, distance is distance. Okay, so it's a very similar form, slightly different meaning to the variables in the formula. Okay, and if we look at this, so electric force varies as inverse square of the distance. That's a similar law as gravity. It's many orders of magnitude, 10 to the 18th times stronger than gravity. So it's much, much, much stronger than gravity. And the big difference is, besides the strength, it also can be attractive or repulsive depending on the situation. So if this situation here, we got two positive charges on a string, they will repel. If we've got two negative charges on strings, they will repel. And then if it's opposite charges, positive and negative, they will attract. So like charges repel, unlike charges, opposite charges attract. Okay, according to Coulomb's law, a pair of particles that are placed twice as far apart will experience forces that are, okay, So it's F equals KQQ over D squared. If we double D, then we quadruple the denominator, which means the force goes down by 4. So 1/4 is strong. Okay, so electrical conductors and insulators, I'll let you guys read all this. The gist of this is that conductors, the electrons can move freely through the material, whereas with insulators, they're locked into place. So a conductor has low resistance to electron flow, and an insulator has super high resistance to electron flow. Okay, some examples. Metals such as copper and aluminum are good conductors. Rubber and glass are examples of insulators. So there's some other things. So semiconductors and superconductors. For semiconductors, they're in this in-between state. They're halfway between insulators and conductors. So sometimes you can dial in exactly if it's a good conductor or bad conductor. And superconductors are strange materials. They have no resistance to current at all. The electrons move perfectly freely through these. We'll get to that in a second. Okay, when you buy a water pipe in a hardware store, the water isn't included. When you buy copper wire, electrons must be supplied by you. No, electrons are in the copper wire. Are already in the wire. Yeah, may fall out. No, never seen electrons fall out of a copper wire. None of the above. So it's going to be B. Okay, so when electric current flows through something, the electrons are already in the material. Okay. Electric field. Okay, so this is force per unit charge. So, well, let's look at these pictures here. For a positive charge, the electric field is radially outward. For a negative charge, it's radially inward. So we want this quantity that doesn't depend on, if we look at this picture over this equation right here, this requires 2 charges. We want to know if we have a single charge, it creates a field in the space around it, that if you brought a charge nearby, it would feel a force. So we think of single charges creating fields around them. And what do we do to calculate that field? Well, we take the force that would be applied to a test charge and divide by the charge of that test charge. Okay, and what this is it's a field in all space surrounding charges that can push and pull other charges around. Okay, so the units are newtons per coulomb. That makes sense. This is a newton. This is a coulomb. So this is newtons per coulomb. It's the direction a positive test charge would be forced if it were placed there. So if we have this positive charge. If we bring in a positive charge here, it's going to shoot off away from it. So the force a positive charge would feel would be away from this positive charge. So the field is away from the positive charge. And then here, if we brought in a positive test charge, it would be attracted to the negative charge because they're opposite. So in that case, the field is in. Okay. The electric field lines of magnitude direction is represented by continuous lines with arrows. It's not vectors. So basically, the closer the lines are together, so if they're close together, then the field is strong. If the lines are far apart, then it's a weak field. So this has a stronger field than this one. Okay. All right, so electric field lines of other configurations. This is a point charge. This is if we have a dipole. This is what the field looks like. This is if we have this polarization here and the field of these arrows here. So with all these different charge configurations, the field can get quite complicated. And these are a few scenarios here. Okay, we have another idea, which is electric potential energy. So before we had gravitational potential energy, or if you lifted something up high, it would have high gravitational potential energy. If you let go, it would fall. Same thing here. So if we have a charge and we put it in an electric field, it has some potential energy. If we let go, it's going to fly in a certain direction. Okay, so let's look at this picture here. If we raise this block up and we cut the cord, then the block will fall. For this, if we have a positive charge and a negative charge like this, we cut the cord, then it's going to fall towards the negative charge. Okay, if this was positive and positive, if we cut the cord, it would fly away. Okay, and this is the idea for springs. If we remember, if we compress the spring, we have higher potential energy here and lower potential energy here. If we take a we have a positive charge and a positive charge. If we move that positive charge here, it's like compressing a spring, adding potential energy to the system. Okay. Last idea is the electric potential. This is a voltage. Okay, so this is energy per charge. And we call it voltage. And so it's electric potential energy per charge. So it's not a field, because a field tells you if you put a charge there, which direction will it feel a force. Okay, it's not that. That's what a field does. What a voltage does is if you put a charge somewhere with a voltage, it tells you how much energy that charge has. Okay, so we have these positive charges here on this ball. We have positive charges on this little rock and positive charges on this little rock. Because they're close to each other, they all have energy. Okay, and if we brought in a new charge in here, it would also have energy. But otherwise, there's voltage all around here. That would be, if we had a charge here, it would have energy. Okay, let's see example. Twice the charge in the same location has twice the electric potential energy, but the same electric potential. So if we bring into this configuration, there's voltage everywhere. If we bring in 1 coulomb of charge, it has 1 unit of energy. If we bring in 2 coulombs of charge to the same spot, we have 2 units of energy. So the voltage doesn't change for that particular spot. But if we bring in different charges, we have different energies. Okay, electric potential energy is measured in joules, that's right. Electric potential, on the other hand, electric potential energy per charge is measured in, we know that's volts. Watts is power, that's energy per time. Amperes is current, electric current. Joules, well, that's energy. Well, we know energy per charge is volts. Okay. Electric potential. So electric potential, high voltage can occur at low electric potential energy for a small amount of charge. High voltage at high electric potential energy occurs for lots of charge. Okay, voltage for different charge configuration, the voltage situation can be extremely complicated. Let's get into some examples of circuits. Okay, so electric current is the flow of electric charge. Okay, and we can often think of a circuit, which is there's a battery and something like a light bulb with current flowing around. We can often think of this in the same way as a pump, which is like a battery. And the current, the electric current flowing in the wires is like water through pipes. And then the bulb is doing something useful for us, which can be resistance to the water flow. Okay, so in this case, the water is flowing downhill, which is analogous to the current flowing through the light bulb. Okay, so let's read these sentences here. Sustained water flow is caused by a source of pressure difference. Okay, so the pump causes a pressure difference, which causes the water to flow. Okay, the battery causes a voltage difference, provides a voltage difference, which causes the electric current to flow. Okay, water current through a device is proportional to the pressure gradient or difference across the device. Okay, so how much water flows through here, through everything here, is proportional to the pressure provided by the pump. And then the current going through the circuit here is proportional to the voltage supplied by the battery. Okay, here water is conserved. What goes in must come out. So water comes in, goes down here, goes through here, back again. So water is not created or destroyed, it just goes around in a circle. Same thing here. The electrons in here just go around in a circle. The electrons aren't created or destroyed. Sustained electric charge flow is caused by a source of voltage difference. Yep, so we said that. So pressure is like voltage. Electric current through a device is proportional to the voltage difference across the device. So pressure difference is like voltage difference. And then charge is conserved, no creation, destruction, or storage. So because no water is destroyed, here it just flows through the circuit. Same thing with charge. Okay, electric current is the flow of charged particles. In metal wires, it's electrons. The protons are bound, so the protons can't move. The electrons move. In liquids, this is like electrolytes. There's lots of positive ions and electrons in the fluid. So it could be complicated how what is carrying the charge. Could be ions that are positive, could be ions that are negative, could be electrons. Each fluid will be different. Okay, rate of electric flow measured in amperes. So the electric current is amps or amperes. That's 1 coulomb of charge per second. The speed of the electrons, called the drift speed through the wire, is very, very slow because the electrons move through the wire, but they're bumping around all the time. So it's like this crazy bumping around of electrons that slowly drift through the wires. Okay, charge flows through a circuit. Voltage is established across a circuit. Okay, so charge flows through the circuit. Voltage by the battery is established on the circuit, or across the circuit is a better word. Okay, the speed and source of electrons in a circuit. The important thing here is when electrons are moving through a metal or any kind of material, they're bumping into a bunch of stuff, so they drift slowly over time as they bump into a whole bunch of stuff in this chaotic motion. So that's the important part, is the electrons are moving extremely fast, but since they're bouncing around so much, they slowly drift through the material. So that's this picture here. So this green is the trajectory of the electron. It's slowly moving to the right, but it's so chaotic. It's hard to say exactly when it's moving to the right. Okay. So when we flip a light switch on a wall and the circuit, an electric field is established inside the conductor. The electrons continue their random motions while simultaneously being nudged by the electric field. Current is established through the wires at nearly the speed of light. So you turn on the circuit, the electric field is quickly established at the speed of light through the circuit, but the electrons are moving drifting very, very slowly through the circuit. It's not the electrons that move at that fast speed, it's the current is established, the voltage is established. It's very, very quickly, but the electrons don't move at that speed. It is the electric field that can travel through the circuit at nearly the speed of light. Okay, if the voltage source is DC, electric fields are maintained and the electrons move in one direction. Okay, we'll talk about AC, which is when the electric field moves back and forth, so the current goes back and forth. Okay, there's some common misconceptions. Let's just read this. Current is propagated through the conducting wires by electrons bumping into one another. That's not true. Electrons are free to move in a conductor and are accelerated by the electric field impressed upon them. I like that. True, they do not bump into one another and other atoms, but this slows them down. True, they do bump into one another and other atoms, but this slows them down and offers resistance to their motion. Electrons throughout the entire closed path of the circuit all react simultaneously to the electric field. That's true. Electrical outlets in the walls of the homes are a source of electrons, not a source of electrons. So it's not true. The outlets in homes are AC, so the electrons move back and forth. And the electrons make no net migration through a wire in an AC circuit. So when you plug a lamp into an outlet, energy flows from the outlet into the lamp, not electrons. So electrons stay in place for the most part. Maybe they move back and forth. But the thing that is carried from the wall socket to the light bulb is energy. So like utility companies sell you energy. Okay. Which of these statements is true? Electric current is a flow of electric charge. That sounds pretty good. Electric current is stored in batteries. That sounds wrong. So batteries provide voltage to a circuit. They don't store current. Sounds like A. Okay. All right, electric resistance. So here we're going back to the water flow example, or analogy, I should say. So the pump provides pressure. The valve is an on-off switch. And the line here is resistance. So the pump pushes water through this high resistance line. So it decreases the energy in the water. Okay, so for the electrical case, so in the water case, this high resistance line is going to warm up. So energy provided by the pump is going to be dissipated by heat through the high resistance line. And then the water comes back into the pump. The pressure is upped again. And it does it again. So for the electrical circuit analogy, the switch is just a switch. You can turn the circuit on and off like a light switch. We have a voltage source, which is like a battery. And then a resistor. It takes energy out of the electric current as it flows through and does something useful with it. It could provide light. It could be a computer providing calculations. It could be all kinds of stuff. So a resistor takes energy out of the current and does something with it. Okay, idea, resists the flow of current. Okay, so their line here resists the flow of the water current, and the resistor here resists the flow of the electric current. The amount of resistance depends on shape and size of the resistor. The longer it is, the more resistance there is. The thicker, the wider, the less resistance. The unit of resistance is ohms. Okay, so if we buy electric resistance, it's going to come in units of ohms. And then this is the symbol in a circuit diagram. Okay, so Ohm's law, let's jump right down here to this equation. The voltage across the resistor equals the current through the resistor times the resistance of the resistor. Okay, so this is probably right here a 3-volt battery, maybe let's say 1.5 volt battery is a 1.5 volt battery. So the current provided by the provided that goes around in this circuit will be equal to 1.5 volts will be equal to the current in that through the circuit times the resistance of the light bulb. Okay, let's do some checking here. When you double the voltage in a simple electrical circuit, you double the current. If we double the voltage, we double the current. The resistance is, if we double the voltage here for this battery, double the current through the whole circuit. So we double the current. Okay. Power. Power is equal to I times V. So if we have one current across 5 volts, that's 5 watts of power. Okay, we talked about this. This is DC, which is we provide a steady voltage and electrons move in a single direction. If you plug into the wall, the voltage is swapping, going back and forth, so the electrons move back and forth in place. Okay, don't talk about much more than that. Okay, for electric circuits, we can hook things up in series. So here's a battery with a switch and 3 light bulbs hooked up in series. So the current flows around this circuit like this, and the current through each one of these light bulbs is exactly the same, because the current coming into one has to equal the current going into the next one, has to equal the current going into the next one, and then around again. So all bulbs connected sequentially. That's this. Total resistance is greater than the resistance of a single bulb. Current is the same through each bulb. If you disconnect one bulb, they all go out. As opposed to parallel circuits. So here, the voltage across each light bulb is exactly the same, and the currents are different. So all bulbs connected to the 2 ends of the battery, so they all have the same voltage. The total resistance is less than the resistance of a single bulb. Voltage is the same across each bulb. Current is divided amongst the bulbs, so the current comes here and splits up 3 ways and recombines to get back to the battery. And if you disconnect one bulb, only that bulb goes out. The 2 others stay lit. Okay. When 2 identical lamps in a circuit are connected in parallel, the total resistance is, so they're connected in parallel, total resistance is less than the resistance of either lamp, so it's A. Okay. Consider a lamp powered by a battery. Charge flows out of the battery and into the lamp. That's not true because it's flowing throughout the entire circuit. From the negative terminal to the positive terminal, in a sense, yes, but it's through the whole circuit. With a slight time delay after closing the switch, it's a very slight time delay. Through both the battery and the lamp. I like that answer the best. So it's flowing around the circuit, through the battery and through the lamp. Okay. All right. Let's just continue with some questions. The net charge of an atom equals, so we're talking about net charge. That's positive, all the positive charges added up minus all the negative charges added up. So it's the net charge, number of protons in its nucleus. That's not right. That would be how many protons it has. The number of electrons surrounding its nucleus. That's not right. 0 if an atom is electrically neutral. That's true. It's not always 0. Sometimes atoms can be stripped of their electrons and become ions. So C is the best answer. If a neutral atom has 22 protons in its nucleus, the number of surrounding electrons is, so it's neutral, so that means net charge is 0. We have 22 protons, which carry a positive charge, And electrons carry the same charge but negative, so we need 22 of them to cancel out the 22 protons. So it's got to be 22 because it's neutral. Okay. When we say charge is conserved, we mean that charge can be saved. No, that's not what we mean. Not created or destroyed. That sounds good. Can be created or destroyed, but only in nuclear reactions. Not sure that's true. Take equivalent forms. I'm not even sure what that means. So B is a good answer. Can't be created or destroyed. A negative ion has more, well, negative means it's got more negative charge than positive charge. So that means more electrons than neutrons? No. More electrons than protons. That sounds good. B. Okay. According to Coulomb's law, the force between a pair of charged particles that are brought closer together. Okay. The force between a pair of charged particles that are brought closer together. Well, that means the force is going to go up. It's going to increase. Okay. It doesn't, if they're the same sign, then the force is going to go up, but it's going to be more repulsive. If they're opposite signs, the force is still going to go up, but it's going to be attractive. But so in either case, it increases. When a pair of charged particles are brought twice as close to each other, the force between them becomes, well, we know this is an inverse square law. So that means if they become twice as close to each other, then they're going to be 4 times. Force will be 4 times as strong. Okay. Unlike Newton's law of gravity, Coulomb's law involves force at a distance, so does gravity. A proportionality constants, one has G, one has K, so they both have that. Inverse square law, they both have that. Repulsive as well as attractive forces, that's the answer. Because Newton's law of gravity only has attractive forces. Coulomb's law has both repulsive and attractive forces depending on the charges. Okay. When you scruff electrons off a rug with your shoes become, so you're pulling the electrons off the rug into your shoes. That means your shoes are going to become negatively charged. Okay. In the electric field surrounding a group of charged particles, field strength is greater where the field lines are. We don't care about the thickness of the lines. We don't care about the length of the lines. Farther apart means weak. Closest means strong. So D is the best answer. A superconductor has the property of changing from a conductor to an insulator. Not necessarily. Becoming conducting when illuminated with light. I don't think that's relevant. Some might, but I don't think so. Having a low electrical resistance, that sounds good. Definitely not all of the above. I don't even like C, which seems like the best answer because a superconductor has 0 electrical resistance, but C is the best answer. Okay. Electric potential and electric potential and electric potential energy are one and the same. That's not true. This is voltage. Electric potential is how much energy there is per charge. Electric potential energy is how much energy there is. 2 terms for the same concept. They're related, but they're not the same. Both of these, so it's none of these. Okay, so electric potential is potential energy per charge. Electric potential energy is just how much energy there is. Voltage is electric potential energy per charge, measured in units of volts. Okay, it's called voltage, gives it away. It's volts. The flow of charge in an electric circuit is much like the flow of water in a system of pipes. That sounds good. Different than water flow in pipes. It is a little different sometimes, but generally it's very good. It's a very good analogy. Like an electric valve, like an electric pump. I'm not sure what those mean. Let's say A is best answer. Electric charge will flow in an electric circuit when electrical resistance is low enough. That sounds good. A potential difference exists. That's even better. The circuit is grounded, not necessarily. Grounded means we stick a pole into the ground and define where our 0 voltage is, but that's a potential difference is most important. Electrical devices in the circuit are not defective. Well, that's important too, but I think B is the critical component. Okay, the electric current in a copper wire is normally composed of electrons. Protons are stuck in the nucleus. Ions, no, it's going to be electrons. Which statement is correct? Voltage flows in a circuit. That's not true. Voltage is provided to a circuit, which causes current flow. Charge flows in a circuit. That sounds right. A battery is a source of electrons in the circuit. That's not true. It's a source of voltage. So B is the best answer. The amount of current in a circuit depends on the voltage across the circuit. That sounds good. Electrical resistance of the circuit. That also sounds good because we have Ohm's law, V equals IR. So the current depends on both the voltage provided and the resistance of the circuit. So I think it's both of these. Okay. When you double the voltage in a simple electric circuit, you double the current. Resistance is dependent on the hardware you used. If you choose a particular resistor, if you want to double the resistance, you have to swap a resistor out. You have to take a 2 ohm resistor out and put in a 4 ohm resistor. So that's determined by the physical part of the circuit. But if I increase the voltage from 2 to 4, then I would double the voltage. Sorry, double the current. So it's got to be A. Okay. When 110 volts are impressed across a 22 ohm resistor, the current in the resistor is, well, we know V equals IR, so voltage equals current times resistance. So that means current will be 110 divided by 22, which is 5 amps. Okay. The difference between DC and AC in electric circuits is that DC, the electrons flow steadily in one direction only. That sounds good. Flow in one direction only. That sounds better. It doesn't always have to be steady. Steadily flow to and fro. To and fro are AC, so it's got to be B. Okay. What travels at about the speed of light in an electric circuit? Charges don't. They have that very, very slow drift velocity. Current is also slow. That goes at a drift velocity, since the electrons are the ones carrying the charge, which causes the current. The field is the best answer. Okay. The drift speed of electrons that make up current in a circuit is not the speed of light. They go very slow. Not even the speed of sound, not even the speed of sound, even slower. Snail's pace. Well, it's not imaginary, so snail's pace is a good answer. It's very, very slow. Okay, so remember, the field quickly turns on at the speed of light, and the current quickly turns on at the speed of light, but the actual electrons are drifting at a snail's pace. Okay, in a simple circuit consisting of a single lamp and a single battery, when current in the lamp is 2 amps, the current in the battery is, okay, so it's a single lamp and a single battery. When current in the lamp is 2 amps, the current in the battery has to be the same. Same circuit. It's got to be 2. Okay. In a circuit with 2 lamps in parallel, if the current in one lamp is 2 amps, the current in the battery is, well, there's 2 lamps in parallel. The current being provided by the battery has to provide current to one lamp and the other lamp. If one lamp has 2 amps, then the 2 lamps together, well, the amount of current has to be more than 2. So it's got to be C. Okay. And that's it. If you guys have any questions, let me know, and I'll see you next time.